There's also synthesis, and that's the 1 over 2 pi right here times the integral from minus infinity to infinity of f of omega times e to the j omega t d omega. Now, why I'm saying synthesis is a lot of times f of omega can represent the filter characteristics that you want. You want an h of omega that's say bandpass filter. Then the bandpass filter function would go in here, and this would be the time domain impulse response. And it's very important to know what the impulse response is, because when you do digital signal processing, what you really do is you have what's called a FIR, it's a finite impulse response filter. So you get the impulse response of the filter, and you cull it down to, say, 1,000 points. It's going to damp out to 0 if it's stable. You use that 1,000 points in the digital domain, in the discrete domain, as something you're going to convolve the signal with, incoming signal, to get the output. You follow me on this? And this is digital signal processing. So it's you have to understand from a Fourier series, or Fourier analysis point of view, and you had FIR filters, didn't you? I talked to you guys.
They are.
Who had me again for signals? You remember that? Finite impulse response?
Yes.
There's infinite impulse response. Those are things that just bounce forever. And then there's finite impulse response that go to 0. Well, everything with, my wife's doing some of this work now. When they do these microcontrollers to do any kind of filter operation, they don't do it with an h of omega. They don't take the Fourier transform or something because they don't have the entire record of it. It's real time. They take a record of the length of the FIR filter's input, maybe 1,000 points, and they operate on that. And they keep on operating on the next point. There's ways to do that. So it's done with, it's a fast time convolver is what it is. Y'all remember convolution, I'll get to that one soon. Yeah, well, you've got to do convolution in the discrete domain for radar processing, or at least appreciate. So with that, here we go through the functional forms we need. First one is this. All right, well, I'll do it right here. Very first thing is delta of t. What does it go to? This is going to be my f of t, this is going to be my f of omega. Well, most of you know that. If I put the delta t in here, right, delta t turns on at 0, right? And the only thing it does is extract the value of any function next to it where it turns on. Here it turns on at 0, e to the minus 0 is 1, so this is 1. And I start there because most people remember that. Y'all remember that one? Next, I talk about a time shift. If I have delta of t minus tau, where tau's in time shift, over here what happens? You guys are very good at saying this. Well, only thing I do is say, where does that turn on at tau, right? It samples the signal, or the thing that's multiplying at that time. It's e to the minus j omega tau. It's still got a magnitude of 1. All right? We'll deal with Laplace. Laplace, by the way, when he mentions Laplace, Laplace is always for designing the actual circuitry and implementing it in stability requirements. The analysis is done in Fourier domain all the time. Now the next thing you do is this. If I have here, it's a pulse of with tau of t. Let me be very clear when I define my pulse. P tau of t pictorially looks like this. Height 1, this is the axis of time, this is minus tau over 2, this is tau over 2, this is p tau over 2, or p tau of t. In the book we're using now, it's defined as rective t over tau, where tau would be the width. The width is in the subscript of the pulse function here, it's inside the argument for the rect function. These are used interchangeably in the journals. Y'all remember that pulse function? How many remember the pulse function, the rect function? Do you remember it or not? No? You don't remember pulse array? Well, you can create this with several different functions. For instance, if I had a u of t function, which is the next one I'm going to do first, this pulse function goes, if you want me to, I'll do it, but it just goes to tau times the sinc of omega tau over 2. And by the way, my definition of sinc function, sinc, write this down, will be sine of x over x. Now there's another definition of sine of pi x over pi x. That's used because that way the zeros, where the function becomes zeros, will be at integer values. This is the definition I'm going to use. And boy, this can be confusing, because some journal articles do not define this as the sink. In his book, and this is something you should, if you have your, are you looking at it online?
Yeah.
Okay, if you, or electronic, if you look online, his definition of the sink is opposite of mine, it's on page 278. But we can adjust for that too. You see it here, sink of z is equal to sink of pi z over pi z. You all see that? I mean, if you.
Oh, yeah.
All right, now, that's not the definition we're using in our signals and systems book, but it was the prior book. And you just gotta modify things and adjust for that, and I'll do that. Are you with me? By the way, if you wanna do this one, just for kicks, because you haven't done these things for a while, we might as well just do one for the good of, I mean, we've done the impulses. Why don't we do this one? So if I want the Fourier transform of this, right? Help me out here, guys. What is it gonna be? Well, the Fourier transform of that pulse function would be the integral from where do I go from where do I go? Well, the magnitude's 1, right? So where do I start the integral at? Minus tau over 2. Where do I end? Tau over 2. Everything else is 0. What am I multiplying by? It's 1 times e to the minus j omega t et, correct? So then what happens? I'll get out of your way, but you can see when I integrate this, I get 1 over minus j omega times e to the minus j omega t, where now t is defined as minus tau over 2, minus tau over 2 to tau over 2, correct, class? I'm going to leave that j downstairs for a moment, and now I'm going to say, well, that's going to be equal to minus 1 over j omega, and then I have e to the minus, or j omega tau over 2 minus e to the plus j omega tau over 2. Please just take a look and convince yourself that's right. Y'all agree with me? Now, what I do next is, I think obvious to most of you, but I'm going to go ahead and make use of that negative sign and switch the positions of these two terms. When I do that, I get this, right? That's starting to look like a function, I know, right? Starting to. I know e to the j theta minus e to the j theta divided by 2j would be sine, wouldn't it? Well, I've got the j right there. The theta is omega tau over 2. So what I'm going to do is move the j omega in here. I want this to be down here, so in a 2. So I have j omega here. Now I've got to multiply by tau. So I've got to multiply by tau here, correct? Top and bottom by the same thing. And then I need to divide by 2. Correct? Now that is what? Well, if I, well, let me just.
Where'd the tau go that was out in the front, Dr. McGinnis?
Yeah, let me do one other thing. But, pardon?
The 2 would be on the bottom.
Tau over 2?
As well.
This, yeah, let me do it this way. When I'm gonna do this, I multiply both by 1/2, right? Okay, right? Top and bottom by 1/2. And that would, I should go for the sign first. If I just take this, yeah, let me do it that way. I had just J omega, sorry, I was gonna go right for the sink. If I just had the J here, and I leave omega here, if you look at this, I really want 2j, don't I? So I multiply by 2 here and here, and now that's a sine. Agreed? Everybody? So I have sine of omega tau over 2. And now I have y2 in front, and I have omega here. That's what's left over once you do the sine transfer. Now I divide top and bottom by 2. Sorry about that. And then I multiply top and bottom by tau. And that is the definition of my sink. So it becomes the sink function, sink of omega tau over 2. How many remember that transform? All right, that's a very important transform. All right, it's used all the time. Then, after that, this is a quick review of signals and systems, we have to go through modulation next. So anytime I have e to the j omega naught t times the function f of t, these are properties. I don't know if you remember that. I could do it with just going right for the cosine, but I'll do this property first. Most of you people seem to remember this pretty well. If I take the Fourier transform of that and use that identity, I can see that I have an integral from minus infinity to infinity. And here it's going to be f of t, but then it's times e to the j omega naught t times e to the minus j omega naught, or omega t dt. That's the Fourier transform of this right here with e to the j omega naught, right? Now, if you look here, I can group the arguments, right? And if I group the arguments, then I have the integral from minus infinity to infinity of f of t times e to the, and now it's going to be minus j quantity omega minus omega naught t dt. And if you look at the definition of the Fourier transform, what you do is transforming a function f of t into this dimension omega. So whatever the coefficient is of the minus jt, that is the transform variable, which means this transforms, not as f of omega, but it would be f of omega minus omega naught. So that's the transform property of modulation with only an e to the j omega naught t. Now, for sake of time, I've got to tell you, y'all know we can do both sine and cosine modulation in terms of that. If I have a cosine of omega naught t, I know that's e to the j omega naught t plus e to the minus j omega naught t over 2. If I have a sine of omega naught t, I know that's e to the minus j omega naught t, e to the plus j omega naught t minus e to the minus j omega naught t over 2, right?
So if you modulate one sine wave with a higher frequency sine wave, the total result is a higher frequency than both of them?
You get sum and difference frequencies, we'll do that.
Okay.
All right. It has to be, if you think about it.
Right, yeah.
And normally what you do is you get, if you have any band limited signal, say the low frequency sine wave, right? It's band limited. What happens when you multiply by a high frequency signal, it shifts the entire band there, its signature, out and centers it at the high frequency. So your upper frequency limit will be the upper frequency limit of the low frequency pulse plus the other one. And that's important to remember. So this goes to just f of omega minus omega naught. And because you all realize if I take this and I multiply a function by it, I've got e to the j omega t over 2 here, and then I've got a minus j omega, e to the minus j omega t here. And what that does, and this is the real modulations I worry about. I don't think I have time to prove that. But if I have, but this you write down, if I have f of t times cosine of omega naught t, that transforms to simply 1/2 f, this is what you're asking about in a sense. It would be omega plus omega naught, and then it's plus f of omega minus omega naught. But the signature of this is very important, so I'm going to stop for a second and mention that.
Communication systems is all just.
Here, I'll put the, a sine wave is basically a cosine wave with a 90 degrees phase shift. So just for completeness, if I put times the sine of omega naught t, that boils down to j over 2 times, and then it would be f of omega plus omega naught. This is important. It's got a minus sense to it. F of omega minus omega naught. Now the reason I'm saying that is the phase is j, and there's subtractive here. It means there's a phase difference in the positive, in the lower frequency versus the upper frequency shift. And that's used for something called Hilbert filtering or Hilbert transforms. Do you have Hilbert transforms yet?
I don't think so.
Okay, well, it's very useful transforms. Okay. So the modulation properties. I want to look at the cosine modulation for a very serious reason. If you have, and there's two factors involved in this, but if you have a baseband signal, this would be in baseband, and remember, baseband to us means this. It means this kind of a look. A signature tau, period t, and then it's the coherent processing interval equal to some m times t, where t would be the pulse repetition interval. You all understand? So if you look at this right here, the baseband signal, if it's infinite, what you're going to get is something that will be limited here. All right, it'd be band limited there. That's actually twice the bandwidth. But no, actually, it is the bandwidth. When you take that signal and multiply it by a high frequency cosine wave, and this is in the omega domain, and this is the, I'll just call it f of baseband of omega. Now, if I take the f of t, baseband of t, and I multiply it by cosine of omega naught t, and here omega naught is going to be much, much greater than b, then what I've effectively done is now I shift, and with radar this is so important, to plus omega naught minus omega naught, and I get the band itself, only if this is amplitude A, this amplitude here is A over 2. This amplitude here would be A over 2. And it would be, it would literally take this, divide by 2, the magnitude, and stick it out there. Now that happens with sine modulation as well. The only thing about sine modulation, it's really something for signal processing purposes. Because of the 90 degrees phase shift that exists there, you can do a whole lot of things to strip out the high frequency signal when you have a sine and a cosine wave at a stable, based on a stable load, local oscillator frequency. You can rip out the high frequency signature, the received wave, and get it down to baseband. Literally, you can create that. And that's so important for radar processing. Because what do we really need when we're talking about target being there now? We need that, right? We need the baseband signature to see if it's above a certain threshold or not. We'd like to strip the high frequency wave up, and we'll get to that too. And I'm just about out of time. I'm going to do one more thing. I was going to do the whole 9 yards on this today. I didn't get to it. Oh, I was supposed to give you a quiz. Oh, it's been one of the mornings up there. More female traffic.
I think we'll forgive.
How about we do Tuesday?
You do a take home.
Forgive.
Next Thursday? No, Tuesday.
When's our spring break? Early March, right?
I think it's first week.
Mid-March.
March.
Second or third week of
Well-
March.
March 7th through 12th.
Man, that's an early spring break. What I don't want to do is schedule anything for that time. I've been up since about 5 this morning, and I've got all sorts of little things that came my way.